Dear students, in today's video we will discuss three topics. First, we will discuss what is electric dipole. Then we will discuss the dipole moment. Then two important board questions, that to calculate the electric field intensity on axial line of the dipole, and the second question, to calculate the electric field intensity on equatorial line of the electric dipole. By watching this video, you will clearly come to know the difference between the axial line and the equatorial line. Let us discuss first topic, what is electric dipole. Electric dipole consists of equal and opposite point charges separated by a small distance. We have two charges. The first charge is plus q, another charge is minus q. Plus q and minus q, both the charges are of same magnitude, that is q, and they are opposite, as one charge is positive charge, another charge is negative charge. They are separated by a distance 2a. At the middle of this line we have a point O. This point O is called center of the dipole. The distance of plus q charge from the point O is a, and the distance of minus q charge from the point O is again a. This O point divides the separation into two equal parts. For example, if you have plus 7 coulomb charge and another charge is minus 7 coulomb, you separate these point charges by a distance of 1 millimeter. 1 millimeter means 10 raised to power minus 3 meter. So this assembly forms an electric dipole. The total charge on the electric dipole can be calculated by knowing that charges can be added algebraically. So the one charge is minus q, another charge is plus q, so their sum will be equal to 0. Similarly, if one charge is plus 7, you add minus 7 coulomb into it, the net charge on the dipole is equal to 0. Next topic is about the dipole moment. Dipole moment is a measure of strength of the electric dipole. It is given as P. P is the representation. P is equal to Q into 2A. P is equal to Q into 2A. So, dipole moment has a magnitude which is equal to product of the magnitude of either charge. Means you can take either plus Q charge or the minus Q charge. One of the charges there, and the distance between them. We have written P is equal to QA, where Q is the charge and this 2A is the distance between the two charges. Dipole moment is a vector quantity. It has direction from negative charge to the positive charge. Let us look at the SI units of dipole moment. As we write down, dipole moment is product of charge and the distance between them. We know that the SI unit for charge are coulomb, and for the distance 2a the units are meter. So the dipole moment has units coulomb into meter. The dimensions of dipole moment can be calculated by starting from the equation of dipole moment, which is P is equal to Q into 2a. For A, the dimensions are length, and for Q, the charge, it is written as product of current into time, because we know that the current is rate of change of charge with respect to time. So current is measured in amperes, so we write A here and the time as a capital T. So it will be ATL, and there is no mass involved, so we write m raised to power 0. L, the power is 1 from here. The T, the power is 1 from here, and A with 1 power. So the dipole moment has this dimensions. Next, what is ideal dipole? It is one of the question asked during the board in previous years. We know that the dipole moment is given as P is equal to Q into 2A. If the Q charge gets very large, if the Q charge gets extremely large and this separation between the charges become very small. At that situation, when Q gets larger and larger and the separation two-way between the charges gets smaller and smaller, during that situation, our arrangement shifts into an ideal dipole. Ideal dipole has almost no size. Next, let us discuss what is dipole field. The dipole field is the space around the dipole in which electric effect of the dipole can be experienced. So, we have this dipole minus Q and plus Q separated by a distance of 2a. Then the field around it, the field around this dipole in which you can experience the electric effect of this dipole is called dipole field. Then let us understand what is axial line and what is equatorial line. This is minus Q charge and this is plus Q charge. They are joined by a line that is two-way. The line joining the minus Q charge and the plus Q charge is called axis of the dipole. This line is called axis of the dipole at which you have placed the charges. If you extend this line and place any test charge, say plus 1 coulomb on this line, then this plus 1 coulomb charge lies on the axial line of the dipole. In simple words, we can say that the axial line is the line which is extended from the line which joins the charges minus Q and plus Q. Another line is the equatorial line. Equatorial line is a line which is perpendicular to the dipole axis. It makes an angle 90 degree to the dipole axis, and this line passes through center of the dipole. It has two conditions. First, it is perpendicular to dipole axis. This is first condition. Second condition, it passes through the center of the dipole. Any point which lies on this line, right, will be called as a point lying at the equatorial line of the dipole. One thing is very interesting to note here that when you put a point on the equatorial line, then this point will have equal distance from both the charges. They will be placed at equal distance. Next, let us start the electric field intensity on the axial line of the dipole. Plus 1 coulomb charge is placed at point P on the axis of the dipole such that the distance of point P from the center of the dipole is R. O is the center of the dipole from here and point P is here and this distance is R. It is clear from the figure that AP is equal to R plus A because R is up to O, then OA plus OP we need to calculate. OA is A and OP. We already know that it is equal to R. So AP is R plus A, while the BP, the distance of plus Q charge from the point P, is equal to R minus A. Now let us calculate the electric field intensity at point P, which has plus 1 coulomb charge at it. Then first we will calculate the electric field intensity due to minus Q charge and we write that as E1 rho. So E1 is equal to 1 upon 4 pi epsilon naught Q. Q is the magnitude of the charge divided by AP square. In the previous page, we have calculated AP is equal to R plus A. So we substitute that value. E1 is along PA because we know that the electric field lines move toward the negative charge. Electric field lines moves toward negative charge. So this E1 is directed toward PA. Then let us calculate the electric field intensity due to plus Q charge. So it will we represented as E2, it is equal to 1 upon 4 pi epsilon naught Q divided by BP square. BP square is R minus A, as BP is the distance between plus Q charge and the plus 1 coulomb charge. So it is along BP. It is away from the plus Q charge. It is along BP. It is written in red color E2. So look at the situation of plus 1 coulomb charge. It has two electric field intensity on it. The first one is which is moving toward the left hand side, and another one is E2 which is moving toward the right hand side. So look at the point P. E1 and E2 are two collinear vectors. Collinear vectors means the vectors which lies on the same line. So this is point P. It has E2 in this direction and it has E1 in this direction. These two vectors are collinear vectors. So as the point P is placed closer to the plus Q charge, so the electric field intensity due to plus Q charge, that is E2, will be higher as compared to E1. The net electric field intensity will be the difference of two, that is E2 vector minus E1 vector. We substitute the value of E2 from here and the value of E1 from here. Then we have this equation. We take 1 upon 4 pi epsilon naught and Q common. So this we will get. Inside the bracket we have 1 divided by R minus A whole square minus 1 divided by R plus A square. This can be solved by using the AB formulas which we did during the 10th class, which is A plus B whole square is equal to A square plus B square plus 2AB. A minus B whole square is equal to A square plus B square minus 2AB, and A minus B and A plus B is A square minus B square. So we utilize all these formulas and simplify the expression for E. So it comes out to be this. Then these terms R square will get cancel out, A square will get cancel out because they are having plus and minus signs. The 2AR and 2AR, these two terms will get added. So we have this expression. Then we know that dipole moment is equal to Q into 2A. This can be utilized over here. Then you will write Q and 2A will go from here and 2R is left only. So it is P into 2R 4 pi epsilon naught divided by R square minus A square raised to power whole square. We know that the dipole is short. This two-way distance is very small as compared to R. So we can neglect A as compared to R. So we can write R square minus A square as R square only, right? So we make this substitution over here. So we will get R raised to power 4 because A square term will get neglected. Then in the bottom we have 4 power and up we have 1 power, so only R cube will be left. So E is equal to twice of P 4 pi epsilon naught dot 1 upon R cube. This E is along BP vector as we did on the figure. This thing is to be noted that at the axial point, electric field intensity is inversely proportional to cube of the distance. So at larger distance from the electric dipole, the dipole field falls more rapidly than for a point charge, because if you are having a point charge, then electric field varies as inverse square of the distance, while the electric field due to a electric dipole varies as cube of the distance when you try to calculate the field strength. The next is field intensity on the equatorial line of the electric dipole. We have an electric dipole which is formed by two charges, minus Q and plus Q. Minus Q charge is placed at A and plus Q charge is placed at B. Distance between A and B is equal to 2A. O is the center of the dipole. This line is the equatorial line which is passing through the center of the dipole. At this line, we have mounted a charge plus 1 coulomb at point P such that AP forms an angle theta on AB. Similarly, BP makes an angle theta on AB. The dipole moment is given by the relation P is equal to magnitude of the either charge, that is Q, multiplied with the distance between the charges 2A. So P is equal to Q into 2A. Now let us see what will be electric field intensity at point P due to the charges of electric dipole. First of all, let us calculate electric field intensity due to minus Q charge. Say electric field intensity due to minus Q charge is given as E1. This E1 will have direction towards PC. So E1 has direction along PC because we know that the electric field lines move toward the negative charge. So it will be directed toward the charge and the direction is PC. Then electric field E1 can be calculated by using this expression, that is 1 upon 4 pi epsilon naught Q divided by the distance between the charges, distance between plus 1 coulomb charge and the minus Q charge, and that distance is AP. So it is AP square. AP can be calculated by using Pythagoras law. This O is the center of dipole, P is the point where plus 1 coulomb charge is placed, and A is the point where minus Q charge is placed. If the total length of the dipole is 2A, then half of the length will be equal to A. OP, we know that we have placed the place charge plus 1 coulomb at a distance R from the origin. Then this AP will be R square plus A square. As we are substituting AP whole square, so we write R square plus A square only. Then what will be the electric field intensity at point P due to plus Q charge? We write it as E2 vector. This E2 vector is oriented towards PD as electric field lines move away from the positive charge. So it has direction away from the plus Q charge, and that is PD. Then the magnitude can be calculated again in the same manner as we did for the minus Q charge. So E2 is equal to 1 upon 4 pi epsilon naught Q divided by BP square. This BP is same as angle is same, and we discussed this BP is equal to R square plus A square as we discussed while defining the equatorial line, that the points are equidistant from the charges. We discussed two electric fields, the one is E1 and another one is E2. To solve the complexity of the figure, we resolve the components of E2 first. E2 has two components. The first component is E2 sin theta, another one is the E2 cos theta. The E2 sin theta is along, this one is the first component, E2 sin theta is along PF, which is straight extension on the equatorial line, and E2 cos theta, another component, is along E2 cos theta is along PR, and such that your PR is parallel to the dipole axis. PR is parallel to the BA, right? So if you extend this thing, then if this angle is theta, this will turn out to be theta 2, as PR and BA are parallel to each other. So here we said two things, that E2 cos theta is along PR and E2 sin theta is along PF. So this is your E2 sin theta and this is your E2 cos theta, right? Now let us resolve the components of first electric field intensity, that is E1. E1 can be resolved into two components. The first component is E1 sin theta. So this is the first component. It is downward and it is E1 sin theta. E1 sin theta is along PE. This is point E, and PE is perpendicular to BA. The second component is E1 cos theta. which is on the same line at which your E2 cos theta was. So E1 cos theta is along PR such that the PR is parallel to BA. So E1 cos theta and E2 cos theta are in same direction and they are on the PR line. E2 sin theta and E1 cos theta are in opposite direction. As you can see, this is point P. E2 sin theta is upward and E1 sin theta is downward, right? So these two will cancel out each other as they are equal and opposite in direction, while E2 cos theta and E1 cos theta are on same line and they are in same direction. So the net electric field intensity will be combination of E2 cos theta and E1 cos theta. We know that magnitude of E1 is equal to E2. So we can simply write it as 2 E1 cos theta. Then we substitute the value of E1 as we calculated, which is 1 upon 4 pi epsilon naught q divided by r square plus a square cos of theta. Then we can substitute the value of cos theta from this Pythagoras. If this is the angle theta, this is point O, this is P and this is A. This we know R and this we have written as A, and this side is r square plus a square. Then the cos of angle are the ratio of base upon hypotenuse. So base is A and the hypotenuse is square root of r square plus a square. So we use that here. Then on little simplification we get this particular result. We know that the dipole length is very small. This A is small, right? We use this particular information that A is very small as compared to R, and we substitute it in the expression. We put P as Q into 2A. So we substitute there, it was having Q cross 2A. This Q cross 2A is equal to dipole moment. This Q cross 2A is equal to dipole moment. So we substitute is equal to P. Then denominator term can be solved as that r square plus a square is nearly equal to r square, because A is very small as compared to R. We substitute this thing here. Then little simplification gives us electric field intensity due to dipole at the equatorial point is given by this relation. Note this thing that electric field intensity varies as 1 upon r cube. In case of electric field intensity due to dipole at the axial point, it was also varies as 1 upon r cube. If we recall the relations again, E equatorial is equal to this, E axial is equal to this. If we divide equation 2 by 1, then we will have E axial by E equatorial is equal to 2. This relation is very important, that the ratio of electric field intensity at axial point and the equatorial point of the dipole is equal to